Hello everyone, welcome to the course Structure Analysis. Myself Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So far we have completed 5 lectures. In that 5 lectures, we discussed about what is meant by structure analysis, and we discussed about the property cantilever, and then how to solve the property cantilever, how to draw the shear force and bending moment diagram. And in today's lecture, we are going to see a different topic, which is kinematic indeterminacy. These kinematic indeterminacy having many applications in not only in the structure analysis. The structure in the sense is not only the buildings, frames or any infrastructures. The structure in the sense the vehicles, the aircraft, the ship, everything is a structure and it is going to have the kinematic indeterminacy. Okay. So in structure analysis, this particular terminology is called as a kinematic indeterminacy. In structural dynamics, this particular terminology is called as a degree of freedom, but both are same only by definition. These are the learning outcomes. So at the end of this lecture, definitely you can able to calculate the degree of static indeterminacy of beams, and also we can able to calculate the kinematic indeterminacy of the beams. Okay. So we are going to discuss with multiple example problems how to calculate the degree of static and kinematic indeterminacy. So you might have observed that this topic is only related to the kinematic indeterminacy, but I would like to discuss about the static indeterminacy also. The reason is, once you understand the concept of the static indeterminacy, so that you can able to easily differentiate, and then you are going to learn what is meant by kinematic indeterminacy. Okay, so that is the reason. So quickly we can go through what is meant by the degree of static indeterminacy. So see the definition. The static indeterminacy of the beam is the number of unknown reactions that exceeded the available equations or available static equilibrium equations. So in the first beginning lecture also we discussed what is the number of available equilibrium equations, that is 3. So one is summation of all the horizontal forces equal to 0, and summation of all the vertical forces equal to 0, and summation of all the moment at any point is equal to 0. So how many equations are there? 3 equations. So any problem which we can able to solve by using these 3 equations alone, that is statically a determinate structure. If any problem we are unable to solve by using these 3 equilibrium equations alone, then that is called as a statically indeterminate structure. So if it is a statically indeterminate structure, what is the degree of that static indeterminacy? That's what we are going to calculate. That is a static indeterminacy. That indeterminacy may be 1 or it may be 100 also. It's depend upon the problem. So one thing I would like to tell you here, the degree of static indeterminacy or kinematic indeterminacy is independent of load. So whatever the beam we are having on the top of that, whether the UDL is there or the point load is there, that is not going to change the degree of static and the kinematic indeterminacy. Okay. So quickly take the example problem, and then we see what is meant by static indeterminacy. So I am going to take the cantilever beam. So this cantilever beam going to have the span L, all those things. Now the degree of static indeterminacy, it is denoted as D suffix S, degree of static indeterminacy, which is nothing but number of equilibrium equations minus number of unknown forces. Okay. So what is the number of equilibrium equations? We know. Otherwise it may be the vice versa also. First we can put the number of unknown forces and then minus number of available equilibrium equations. Okay. So we need to understand what are the unknown forces are there acting in the structure first. Since it is a fixed support, we are going to have the vertical reaction VA, horizontal reaction HA, and then the moment MA. So how many reaction forces are there? Let's say this is 1, the horizontal force is 2, and then moment is 3. So totally 3 unknown forces are there. So we know the number of available equilibrium equations are 3 and the number of unknown forces are 3. So this sum up I am getting 0. This 0 represents the structure is statically a determinate structure and the degree of static indeterminacy is 0. So there won't be any additional equations are required. Only the equation summation of all the horizontal forces equal to 0, summation of all the vertical forces equal to 0, summation of all the moment is equal to 0. These equations are alone is sufficient to solve this problem. Okay, so this is the degree of static indeterminacy. So what is a static indeterminacy? Static indeterminacy is nothing but the difference between the available equilibrium equations and then the number of unknown forces acting in the structural system. So we may discuss many problems also like this for a static indeterminacy, but our topic is a kinematic indeterminacy. We'll go there and then we'll see what is the difference between the static indeterminacy and then the kinematic indeterminacy. Let's go through the definition of the kinematic indeterminacy. The kinematic indeterminacy is defined as the number of unknown joint displacement or degree of freedom which are required to be known to proceed with the analysis of the structure. So it's clearly visible here. What is that? The kinematic indeterminacy are related to unknown joint displacements. The kinematic indeterminacy are related to unknown joint displacement. So if you take a structural system, whatever the forces acting in it, that is unknown. Whatever the displacement it is subjected to, that is also unknown. So in this case, now you understand the difference. Static indeterminacy means it only deals with the number of unknown forces. Kinematic indeterminacy means it is deals with the number of unknown displacements. And it is also called as a degree of freedom. Degree of freedom means the number of independent coordinate required to specify the motion of the system. So this definition we used to describe in structural dynamics. For structural analysis, we are going to use the definition, the number of unknown joint displacements. So quickly we are going to discuss n number of numerical problems. With that we understand what is this kinematic indeterminacy. So let's take a beam. So this is my beam. I am having the roller support and another hinged support here. You might have observed that on the beam I am not drawing any loads. The reason is whether load is there, whether load is not there, the static and kinematic indeterminacy is not going to differ because it is depends upon the support conditions. Okay, so here two supports are there, one is roller support and then another one is a hinged support. So in structural analysis, we are considering each joint going to have the 3 degree of freedom. What is the 3 degree of freedom? The any joint can move in a horizontal direction. Any joint can move in a vertical direction. Any joint can able to rotate also. The joint can able to rotate. The joint can able to move in a horizontal direction. The joint can able to move in the vertical direction. So we consider every joint going to have the 3 degree of freedom. So I am going to write the equation, that is 3 degree of freedom we have. So 3 times of number of joints, then minus number of reaction forces small r plus summation of m dash minus 1. I will tell you how this equation came. So let's explain. This is the number of joints. This 3 is nothing but 3 displacements are possible. Every joint 3 displacements are possible. R is the unknown reaction forces and this m dash minus 1, whenever we have the internal hinge, we are going to have this term. So whenever we are going to have the internal hinge, then only we are going to get that term. 3 times of joints. Can you tell me how many joints are there in this beam? This beam, let's say this is joint A, joint B and joint C. One may ask, sir, joint A having the support, it may be considered as a joint. Joint B having the support, it might be considered as a joint. But why the free end is a joint? So in structural analysis, free end also is considered as a joint. The reason is that free end is going to deflect in a downward direction. So there is a displacement over there. Okay, there is a displacement over there. That's why we are considering the free end is a joint. So number of joints are 3. Let me write down here joint 1, joint 2, joint 3. So 3 joints are there minus reaction forces. This is a very important. I am going to mark the reaction forces. At support A, one vertical reaction is possible. There won't be any horizontal reaction. The reason is it's a roller support. It can able to move in a horizontal direction. It won't resist that horizontal movement. So there won't be any reaction forces. So only one vertical reaction. Coming to the support B, it is a hinged support. One vertical will be there. One horizontal reaction force will be there because it is held in position, it can rotate, but it won't allow the horizontal movements. Okay, so totally how many reaction forces are there? Let's mark it here. This is 1, this is 2 and this is 3. Totally 3 reaction forces. And then in this problem, if you see, we don't have any internal hinges. So this term plus summation of m dash minus 1 is not applicable. Okay, so I am writing 3 multiplied by 3 is 9 minus 3 will be having 6 degree of freedom. Now I am going to discuss about the axial deformation. For example, you consider this is a beam having a simply support condition. If the beam is loaded, it is going to deflect. Okay, but in addition to that, this beam may be pulled or it may be pushed. Either the beam may be going to subjected to the tensile force or the compression force also. But in the beams and portal frames, this either the compression of this beam along the length or the tension, which is considered as axial deformation, is negligible. Since the axial deformations are negligible, we are going to deduct that value. So how many members are there here? How many spans are there? Span 1, span 2. So this member going to elongate and this member going to elongate. We are not going to consider the axial deformation. Why we are not considering the axial deformation? Because the axial deformations are negligible in the beam. Or other words, the elongation and contraction of the beam is negligible. Okay, we consider axially, beams are axially rigid beams. So totally I got 6, 6 minus 2 span is there, 2 members. So 6 minus 2 will be getting 4 if you neglect the axial deformation. Otherwise, it is simply 6. So let's discuss about the next one. We'll take a next example. This time we will take an internal hinge. So I am taking a beam having the roller support here and hinged support here. In between, I am providing one internal hinge. Internal hinge means what? It will rotate like this in that hinge. Okay, let's quickly apply this formula. 3 times of j minus r plus summation of m dash minus 1. So this is the formula we are going to apply. Let's calculate 3 times of joint. How many joints are there in this beam? So this is the joint 1, let's say A. The hinge is a joint B and this is joint C. So totally 3 joints are there. Degree of kinematic indeterminacy. So 3 multiplied by 3 minus reaction forces. What is the reaction forces here? 1 vertical here and then 1 horizontal here. So totally 1, 2, 3. The internal hinge is not a support. It's not going to transfer any reaction forces. Okay. So totally how many reactions? 3 reactions. Now this term also we are going to discuss because this is having the internal hinge. So here the m dash is nothing but number of members connecting to the hinge. So how many members are connecting to this internal hinge? This is the member 1, this is the member 2. 2 members are connecting. So plus 2 minus 1 from the formula. Okay. So we'll be getting 9 minus 3 plus 1. So we will be having 7. So 6 plus 1 will be having 7. So neglecting axial deformation, then it is 7 minus 1, 6. Why? Because one span is there. So this internal hinge, the entire span is considered as a one member which is going to have the axial tension or axial compression. That is axial deformation. Okay. So if you neglect it, then it is 6. If you are not neglecting, then it is 7. Okay. Take another example. We have a hinged support. We have roller support. Let's have another roller support. Okay. Now, I am placing the internal hinge exactly at the middle of the support. Let's write the equation. 3 times of j minus r plus summation of m dash minus 1. 3 times of joints 1, 2, 3 joints. So 3 minus reaction forces. What are the reaction forces? Here one vertical, one horizontal because injet support, roller support only one vertical. How many reaction forces? 1, 2, 3 and 4. It's very easy. So 1, 2, 3, 4. 4 reaction forces are there here and then plus summation of m dash minus 1. Number of members connecting to the internal hinge. Member 1, member 2. 2 members are connecting. So this is 2 minus 1. So degree of kinematic indeterminacy equal to what value we are getting here? So 9 minus 4 plus 1 will be having 6. So this is without neglecting the axial deformation. If you neglect the axial deformation, then 6, how many members? 2 span is there. This is the span 1 and this is the span 2. So minus of 2, after neglecting the axial deformation, the kinematic indeterminacy is 4. Let's discuss the another problem, one more problem. Let's have the propped cantilever with the internal hinge at center. Okay, let's quickly calculate this problem. Formula is 3j, degree of kinematic indeterminacy equal to 3j minus r plus summation of m dash minus 1. Okay, so 3 times of j. Let's put joint. This is the joint 1, joint 2, joint 3. So 3 joints minus reaction force is a fixed support, one vertical reaction, one horizontal reaction and one moment will be there. So in right hand side we have only the roller support, only one vertical reaction is possible. How many reaction forces here? 1, 2, 3, 4. So 4 reaction forces, 4 plus summation of m dash minus 1. What is the m dash here? Number of members connecting to the internal hinge. So this is the one member and this is another member. Totally 2 members are connecting. So this is 2 minus 1. So 3, 3, we are going to get 9. So 5, from here we will be getting 1. So 4 plus 1 we will be getting 5. This is 4 and then we will be getting a 1. So 5. So 9 minus 5 will be getting 4 degree of kinematic indeterminacy. Okay. Now, if you neglecting the axial deformation, then the degree of kinematic indeterminacy. Then for how many span is there? This is the span 1. The span 1 comprises of one member with the internal hinge. So 4 minus 1 equal to 3. So this is the answer. So in this way, we can able to calculate the degree of static indeterminacy and kinematic indeterminacy for a beam. Okay, I hope this lecture is helpful for you to understand the concept of degree of static indeterminacy and kinematic indeterminacy. Thank you.